You are like my nephews, and I'm here to share the stories of the universe with you. I'm trying my best to explain how space grew, how light began its journey, and how galaxies, stars, and planets came to be. Together, we will explore the quiet, hidden forces that shaped everything around us, traveling from the tiniest ripples of energy to the vast, silent expansion of the cosmos. Please share in the comments from where you are watching this documentary. The universe began to grow in silence. Space itself stretched outward, expanding in ways that would define the scale of everything to come. There was no light, no sound, no matter as it is known today, only a vast, empty expanse pregnant with possibility. Within this emptiness, the fabric of space quietly unfolded, laying the groundwork for the structures that would one day populate the cosmos. During this earliest stage, expansion was imperceptible in scale, yet immense in significance. Space did not rush or collide. It expanded uniformly, a steady growth without disturbance. Even though nothing could be observed, the universe was active at a fundamental level. Tiny fluctuations in energy and density appeared, imperceptible ripples that would later become the seeds of stars and galaxies. These fluctuations were minute, but their influence would shape the cosmos on scales beyond imagination. The expansion of space was accompanied by the interplay of energy and the fundamental forces of nature. Gravity, though subtle at this stage, began its slow, patient work of guiding matter toward structure, while the uniform stretching of space ensured that energy and potential were distributed across the growing universe. The earliest instance contained the blueprint of all cosmic architecture, the future clusters of galaxies, the interwoven filaments of matter, and the vast cosmic voids that would emerge in billions of years. Even in the absence of visible matter, the universe exhibited order. Quantum fluctuations introduced tiny variations in density, like imperceptible ripples on a still pond. These variations would later amplify under the influence of gravity, guiding the assembly of stars, galaxies, and larger structures. The universe was learning its own laws, the silent mechanics of creation, unfolding with absolute precision. Space continued to stretch. Though there was no motion in the traditional sense, distances between points increased, and the potential for matter to coalesce grew. In this period, energy and space were intimately linked. The expansion itself carried energy across the newborn cosmos. The scale of the universe grew faster than intuition could grasp, yet every growth was balanced by the fundamental principles that would persist throughout cosmic history. The quiet expansion also set the stage for time. As space stretched, the passage of time began to acquire meaning, providing a framework for events to unfold in sequence. Even though nothing yet existed that could perceive this progression, the universe was already evolving. The earliest instance contained within them the mechanisms that would eventually produce light, atoms, stars, and planets. This silent growth was the foundation for everything that followed. From these imperceptible motions, the structures of the cosmos would emerge. The universe was vast even before it had visible form, and within its emptiness lay the potential for all matter, energy, and life. The quiet stretching of space marked the beginning of a process that would continue indefinitely, carrying the cosmos from simplicity to the complexity observed today. The whisper of the void was not sound, but movement, not noise, but change. It was the universe learning to expand, to grow, to become. Every subsequent star, galaxy, and planet traces its origin to this subtle unfolding, the first act of creation occurring in silence, invisible yet absolute. In this moment, the universe existed as a vast, expanding potential, a stage set for the emergence of all that would follow. Space itself began to stretch, growing in a sudden, remarkable expansion that transformed the fabric of the universe. This period, known as cosmic inflation, occurred in a fraction of a second, yet its consequences were enormous. Distances between regions of space increased exponentially, faster than the speed of light, creating the vast, uniform expanse that would form the stage for all cosmic structures. It was not a movement of matter through space, but of space itself, stretching, carrying energy and potential across the newborn cosmos. During inflation, quantum fluctuations imprinted tiny variations in energy and density onto the expanding space. These fluctuations were minute, barely perceptible, yet they would become the scaffolding for future galaxies and clusters. Regions of slightly higher density began to gather matter once gravity took hold, while lower density regions remained sparse. The universe was developing a pattern, a subtle order arising from randomness, guided by the fundamental forces at work even in the earliest instants. The expansion was both immense and silent. There was no heat, no light, no sound to mark the event. It unfolded in absolute invisibility. Space stretched uniformly in all directions, a growth so extreme that points initially close together were flung apart faster than the speed at which light could travel. Yet this rapid stretching did not destroy coherence. It preserved the quantum fluctuations that would serve as the seeds of cosmic structure. The universe was simultaneously smooth and lumpy, homogeneous on large scales, but with tiny variations that held the blueprint for everything to come. Energy density dominated the young universe. The vacuum itself contained an enormous amount of potential energy, driving the expansion and shaping the geometry of space. This energy was uniform yet dynamic, causing space to inflate at an extraordinary rate. The process smoothed out irregularities, creating a cosmos that would appear remarkably even across vast distances while maintaining the seeds of future structure. Inflation was brief in duration, yet the effects would persist for billions of years, establishing the large-scale uniformity of the universe. The scale of inflation is difficult to imagine. Regions that were once smaller than a single atom expanded to sizes far beyond our observable universe in an instant. Despite the rapid growth, the universe remained incredibly ordered at large scales, with the laws of physics applying uniformly across every emerging region. It was a delicate balance between expansion and the underlying fluctuations, a harmony that would govern the formation of galaxies, stars, and planets. After inflation ended, the universe had grown enormously, but remained almost completely empty. Energy began to convert into matter and radiation, setting the stage for the first particles and eventually photons to move freely. The foundation of cosmic structure had been laid, invisible yet precise. The rapid expansion had stretched the initial fluctuations across vast distances, planting the seeds for galaxies and clusters to emerge billions of years later. This first stretch of space illustrates the remarkable interplay between energy, geometry, and the laws of physics. Space itself was active, dynamic, and capable of shaping matter before it existed. The universe in its infancy was already demonstrating principles that would govern its evolution for eons to come. Every galaxy, star, and particle traces its origin to this silent inflation, the first grand growth of space that transformed nothingness into a cosmos ready to host creation. The universe had begun its journey from nothing, yet in its silent expansion it carried the blueprint for everything. Space was no longer empty, it was alive with potential, stretching outward with the promise of stars, galaxies, and worlds yet to form. This first expansion marked the beginning of cosmic history, the moment when the universe became more than an idea and started to become a reality. After space had stretched and inflation ended, the universe remained a dense, hot fog of energy and particles. Photons, the particles of light, were trapped, scattering continuously off free electrons and atomic nuclei. Light existed, but it could not travel freely. The cosmos was opaque, a vast glowing soup in which radiation and matter were tightly coupled. In this early phase, energy was everywhere, but information could not propagate across distances. The universe was effectively dark despite its brilliance. As the universe expanded, it cooled. The energy density decreased and temperatures fell, allowing particles to combine. Electrons bound to protons and other nuclei, forming neutral atoms in a process called recombination. With the formation of these atoms, photons were no longer constantly scattered. Suddenly, they could move freely across space. The universe became transparent, allowing light to travel vast distances for the first time. This moment, known as the decoupling of matter and radiation, transformed the cosmos from an opaque haze into a vast, luminous expanse. The travel of light marked a fundamental transition. Photons, once confined, now carried information about the early universe, encoding the patterns of density fluctuations imprinted during inflation. These fluctuations would become the blueprint for the first galaxies and clusters. The cosmic microwave background, the faint afterglow of this event, remains detectable even today, providing a snapshot of the universe at a time when it was only a few 100,000 years old. It is the earliest light, traveling uninterrupted across billions of years, allowing the universe to communicate its infancy across time and space. The release of photons was not violent. There was no bang or explosion, only a quiet emergence of light from within the expanding cosmos. The cooling process had allowed the universe to organize itself, creating conditions suitable for structure to form. Temperature differences became significant, guiding the flow of energy and the aggregation of matter. Regions slightly denser than their surroundings began to attract more matter under gravity, initiating the slow, patient formation of the first cosmic structures. The implications of light traveling freely were profound. With transparency, radiation could now interact with matter across distances, distributing energy and influencing the formation of structures. The universe entered a new era in which photons could propagate and matter could begin to assemble in the patterns dictated by the earlier quantum fluctuations. Space had matured into a stage where both light and matter could exist independently, allowing complexity to emerge from the once featureless void. Observing this light today, billions of years later, provides a window into the universe's formative moments. Each photon carries a story, tracing its origin to an era when space and energy were intimately coupled. These earliest photons set the pace for cosmic evolution, marking the transition from a featureless, opaque expanse to a universe capable of forming stars, galaxies, and planetary systems. The journey of light is ongoing. Photons continue to traverse the cosmos, expanding alongside space, carrying information about the structure and evolution of the universe. From the first scattering to free travel, the emergence of light represents a critical step in cosmic history. It transformed the universe from a dense, chaotic energy soup into a space where structures could form and life could eventually emerge. In this moment, light became a messenger, carrying the imprint of the universe's earliest stages across the vast emptiness. The silent expansion continued, but now it was illuminated, revealing patterns and potential. The universe had learned to shine, and with this illumination came the possibility of observation, understanding, and the slow unfolding of cosmic history. As the universe expanded and photons began their journey, temperature became one of the most critical factors shaping the cosmos. In its earliest stages, the universe was unimaginably hot, with energy so intense that particles could not combine. Protons, neutrons, and electrons collided constantly, prevented from forming stable atoms. Matter and radiation existed in a dense, chaotic mixture, a high-energy plasma in which structure could not yet emerge. The behavior of the universe at this time was dictated entirely by temperature, which controlled the formation, interaction, and movement of particles. As expansion continued, the universe cooled. This cooling was gradual but relentless, lowering the average energy of particles and allowing new possibilities to emerge. Electrons began to combine with protons, forming neutral hydrogen atoms. Helium and trace amounts of lithium also emerged from nucleosynthesis. This process, delicate and precise, depended entirely on the rate at which the universe cooled. Too fast, and atoms could not form. Too slow, and the balance of elements would differ. The temperature set the rhythm for creation, a cosmic metronome guiding the assembly of matter. Cooling also allowed photons to travel freely for the first time. Before this, radiation was trapped in a dense plasma. Light could not propagate without constant scattering. As the universe cooled below critical thresholds, photons decoupled from matter, creating the cosmic microwave background, a fossil imprint of the universe at that stage. These photons carried information about temperature variations, tiny differences that seeded the structures of the cosmos. The universe, in essence, began to record its own history in the patterns of light and temperature. The distribution of temperature was not uniform. Slight fluctuations created regions of slightly higher or lower energy, which would influence the later formation of galaxies. These variations, amplified over billions of years by gravity, created the cosmic web, filaments of galaxies separated by vast voids. Temperature was more than heat. It was a sculptor shaping the density, motion, and organization of matter. The universe's eventual architecture was encoded in the thermal patterns of its infancy. Even subtle differences in temperature determined the chemical composition of the universe. The ratio of hydrogen to helium, the abundance of trace elements, and the distribution of matter all depended on these early conditions. Tiny changes in energy could have prevented the formation of stars or altered the evolution of galaxies. Temperature was the silent architect, its influence omnipresent and absolute, guiding the universe toward the complex structures we observe today. Temperature also set the pace for expansion. As the universe cooled, energy density decreased, slowing the rapid early growth and allowing gravity to begin its work in assembling matter. Stars could eventually ignite, galaxies could form, and planetary systems could emerge, all because the universe cooled at a precise rate. It was an interplay of energy, space, and time, with temperature as the mediator of cosmic possibility. The temperature of creation illustrates that even invisible factors can have monumental consequences. It shaped the behavior of matter, influenced the flow of radiation, and established the conditions necessary for all future cosmic structures. Without this cooling, photons would remain trapped, atoms could not form, and the universe would remain a chaotic plasma, incapable of producing stars or galaxies. In this process, the universe demonstrated remarkable precision. Small variations in temperature, imperceptible yet significant, created the seeds of galaxies and the framework for cosmic evolution. Cooling transformed chaos into potential and potential into structure. The universe, once an undifferentiated hot soup, now held the foundations of order, guided entirely by the quiet influence of temperature, a force that determined the very architecture of everything to come. As the universe cooled and light began to travel freely, periods of relative calm emerged amidst the ongoing formation of matter. These moments, though subtle and quiet, were essential for the growth of structure. Between bursts of energy and the rapid movements of particles, the cosmos experienced stretches of stillness, a kind of cosmic pause that allowed matter to organize, atoms to coalesce, and the earliest seeds of galaxies to take shape. Even in a universe dominated by immense forces, these intervals of quiet were crucial. During these calm periods, density fluctuations, seeded during the inflationary expansion, began to manifest more clearly. Regions slightly denser than their surroundings started to attract more matter under gravity. Gas clouds could gather and stabilize, and the first protostructures took form. The universe was not static. It remained dynamic, yet the rhythm slowed enough for patterns to emerge. In these intervals, the fabric of space and matter became organized, preparing for the complex structures that would follow. The calm was not emptiness, but opportunity. Without these quiet phases, energy and motion would overwhelm the delicate processes of formation. Stars could not ignite, galaxies could not form, and the intricate cosmic web would never emerge. It was a balance between motion and stillness, a subtle orchestration that ensured the universe would evolve in an ordered manner rather than descending into chaos. The pauses allowed gravitational forces to operate effectively, guiding matter into coherent structures. These intervals also allowed temperature to stabilize in regions of space, enabling atomic interactions to proceed without disruption. Hydrogen and helium gas clouds could cool, condense, and eventually collapse under gravity. The cooling was gradual, measured in millions of years, yet it was decisive in shaping the early universe. Each pause amplified the effects of small variations, ensuring that the quantum ripples from the universe's earliest moments could grow into stars, galaxies, and clusters. The calm between explosions also facilitated the first movements of matter on large scales. Gas clouds began to rotate slightly, forming the proto-rotations that would later become spinning galaxies. Collisions were rare and interactions gentle, allowing the organization of matter to progress. These quiet phases created the conditions necessary for the first gravitational wells to develop, regions in which matter would accumulate over billions of years, eventually producing the luminous structures visible today. Even today, the universe retains the imprint of these pauses. The large-scale distribution of galaxies, the vast voids between filaments, and the overall uniformity of the cosmic microwave background are all evidence of the periods when the cosmos was able to organize itself without disruption. The calm was a silent partner to the universe's more violent events, demonstrating that growth often requires patience and balance. In essence, the quiet of the universe was never empty. It was active in subtle ways, shaping matter, guiding energy, and enabling the first structures to emerge. Between bursts of formation and movement, the cosmos developed the conditions necessary for complexity. The calm between explosions allowed order to arise from chaos, forming the scaffolding for the galaxies, stars, and planetary systems that would follow. This interplay of motion and stillness illustrates a fundamental principle. The universe grows not only through dramatic events, but also through quiet intervals in which forces operate subtly yet effectively. The calm between explosions was a crucial stage in cosmic evolution, ensuring that the universe could transition from a hot, dense plasma into a structured, luminous expanse capable of supporting stars, galaxies, and eventually life itself. Within the quiet, expanding universe, tiny fluctuations in density began to grow. These minute differences, almost imperceptible at first, became the seeds of galaxies. Regions slightly denser than their surroundings attracted more matter under the influence of gravity, drawing gas and particles together into small, organized structures. The universe was shaping itself, converting initial chaos into patterns that would eventually give rise to stars, clusters, and the grand formations visible today. The process was gradual. Gravity acted slowly, pulling matter inward, while the universe continued to expand outward. Denser regions became increasingly dense, forming protogalaxies and gas clouds capable of further collapse. Even small variations in density resulting from quantum fluctuations during inflation had amplified over millions of years, creating the cosmic scaffolding upon which galaxies would be built. The largest structures of the universe began as almost invisible ripples in space. Gas clouds condensed within these gravitational wells. As they cooled, they became more compact, preparing the conditions for the first stars to ignite. The initial structures were irregular and diffuse, but over time, rotations emerged. Proto-galaxies began to spin, acquiring the angular momentum that would later define spiral and elliptical galaxies. The process was meticulous and precise, guided entirely by the forces of nature and the initial distribution of matter. The seeds of galaxies were not uniform in size or shape. Some regions contained more matter and would form massive clusters, while others remained sparse, destined to become the voids between filaments in the cosmic web. This non-uniformity was essential for creating diversity in galactic structures, allowing galaxies of different sizes and types to emerge over billions of years. Even the largest galaxies in today's universe trace their origins to these early density fluctuations. The influence of dark matter played a crucial role in this phase. Invisible yet omnipresent, dark matter provided additional gravitational pull, stabilizing forming structures and helping matter accumulate. Without dark matter, these seeds might not have grown efficiently, and the universe would lack the coherent galaxies and clusters observed today. It acted as a silent framework, guiding baryonic matter into the shapes that would define the cosmos. Over time, proto-galaxies merged and interacted. Small clumps combined to form larger systems, collisions became common, and the structure of the universe became increasingly complex. Yet this complexity originated from the simplest beginnings, tiny, almost invisible variations in density that grew steadily under the persistent influence of gravity. The universe demonstrated a remarkable capacity for self-organization, transforming imperceptible ripples into vast cosmic structures. The seeds of galaxies illustrate a fundamental principle of cosmic evolution. From small, nearly invisible beginnings, immense structures can emerge through the interplay of simple physical forces. Matter organizes, energy moves, and gravity sculpts, all within the framework of an expanding universe. The first seeds planted during this phase would grow into galaxies containing billions of stars, each a potential host for planets and eventually life. In this stage, the universe began to resemble the cosmos we observe today. The blueprint for large-scale structure was established, with filaments, clusters, and voids already taking shape. Though invisible to any observer at the time, these seeds contained the promise of the grandest creations, demonstrating that even in silence and stillness, the universe was capable of extraordinary growth. As the seeds of galaxies began to grow, two fundamental forces quietly shaped the evolution of the universe: gravity and time. Gravity, the invisible force pulling matter toward matter, dictated the assembly of structures across vast distances. Time, intertwined with space itself, provided the framework in which these processes could unfold. Together they acted as the hidden architects, sculpting the cosmos with precision and patience. Gravity was the primary agent of organization. Regions with slightly higher density attracted more matter, amplifying the differences in the distribution of energy and mass. Gas clouds collapsed under gravitational pull, forming the first protostars and clusters. Galaxies emerged as matter coalesced, shaped by the intricate balance of gravitational forces. Even dark matter, unseen and undetectable by light, contributed significantly to this process, forming the invisible scaffolding that held the emerging cosmic structures together. Time played a subtler yet equally vital role. The expansion of the universe stretched space, but the passage of time allowed matter and energy to evolve in a predictable sequence. Processes that seemed instantaneous on atomic scales unfolded over millions of years on cosmic scales. Stars ignited, exhausted their fuel, and collapsed into remnants, while galaxies merged and reorganized. The flow of time ensured that events occurred in a coherent order, enabling complexity to arise from simplicity. The interplay of gravity and time also governed the motions of galaxies. As proto-galaxies formed, they began to rotate, acquiring angular momentum that influenced their shape and internal dynamics. Collisions between structures were guided by gravitational forces, producing spirals, ellipticals, and irregular galaxies. These interactions, although violent on local scales, were part of a larger pattern dictated by the slow, steady influence of the universe's fundamental forces. Even on the largest scales, gravity and time maintained balance. While expansion pushed galaxies apart, gravitational attraction held clusters and filaments together, creating the large-scale web of the cosmos. This delicate equilibrium allowed the universe to grow in both size and complexity, a structure emerging from the interaction of forces operating silently yet relentlessly. The patterns observed in the cosmic microwave background, the distribution of galaxies, and the formation of clusters all bear the signature of this interplay. The influence of these hidden architects extended to the formation of stars and planetary systems. Gravity pulled gas and dust into dense cores, triggering nuclear fusion that ignited the first stars. Time allowed these stars to evolve, enriching the surrounding medium with heavier elements through supernovae. This process created the conditions necessary for the eventual emergence of planets, atmospheres, and the chemical precursors for life. Gravity and time also governed the life cycle of galaxies. Mergers and interactions shaped their growth and evolution, while gravitational forces stabilized structures within clusters. Time dictated the pace of change, allowing slow processes to accumulate, producing complexity over billions of years. The cosmic dance of attraction and repulsion, of growth and equilibrium, unfolded in a precise, predictable manner. Together, gravity and time transformed the universe from a nearly uniform expanse into a structured, evolving cosmos. The unseen hand of gravity guided matter, while a steady passage of time allowed complexity to emerge. These hidden architects operated without sound or spectacle, yet their influence is imprinted across the cosmos, from the largest clusters to the smallest stars. The universe, shaped by these forces, demonstrates that creation is not only the result of explosive events, but also of persistent, quiet processes acting over immense scales. Gravity and time, in concert, built the stage upon which galaxies, stars, and planetary systems would emerge, ensuring that the cosmos could evolve from simple beginnings into the intricate, expansive universe observed today. The universe continued to expand, slowly and steadily, like a gentle waltz that stretched across unimaginable distances. This expansion was not explosive, but measured, unfolding over billions of years. Space itself grew, carrying galaxies with it, even as gravity worked locally to hold stars, clusters, and galactic structures together. The rhythm of this expansion shaped the cosmos, allowing structures to form and evolve without being torn apart. Galaxies drifted apart, their relative motion guided by the stretching of space. At the same time, local gravitational attraction bound clusters and filaments into the cosmic web. This interplay created the large-scale patterns observed today. Vast filaments of galaxies separated by immense voids. Expansion set the stage for the universe's architecture, a dynamic equilibrium between separation and cohesion, motion and stability. Light traveling through space also reflected this growth. Photons emitted from stars and galaxies were stretched along with space itself, shifting toward longer wavelengths in a process called redshift. The universe's expansion left its imprint on light, allowing future observers to measure distances, velocities, and the rate of cosmic growth. Even the faint afterglow of the cosmic microwave background carries evidence of this gradual stretching, a subtle record of the universe's earliest expansion. The slow music of expansion also influenced the formation of galaxies and clusters. As distances between structures increased, interactions became less frequent, allowing galaxies to evolve more quietly within their local environments. Star formation, mergers, and rotational dynamics continued, but the expansion provided breathing room, preventing overcrowding and enabling stable, long-term development. The universe was learning to pace itself, creating complexity without chaos. Expansion also determined the distribution of matter. Regions with higher density remained gravitationally bound, while less dense areas stretched apart, forming the vast cosmic voids. The interplay of expansion and gravity produced the characteristic patterns of the cosmic web, an intricate network that spans the universe. Each filament, cluster, and void traces its origin to the balance between these two forces, a silent choreography that unfolded over billions of years. Even as space stretched endlessly, the universe maintained coherence. Structures held together despite the vast distances, demonstrating the subtle harmony between expansion and attraction. Stars ignited, galaxies rotated, and clusters remained bound, all moving within an ever-growing space. Expansion shaped not only the positions of objects, but also the context in which cosmic evolution occurred, providing the backdrop for all subsequent events. This slow music of expansion reminds us that the universe grows not through forceful explosions alone, but through steady, persistent change. The waltz of space carries galaxies, shapes patterns, and structures the cosmos over time, creating the framework for complexity to emerge. Expansion is silent yet absolute, a cosmic rhythm that has guided the universe from its earliest moments to the vast, structured expanse observed today. The universe continued to expand, slowly and steadily, like a gentle waltz that stretched across unimaginable distances. This expansion was not explosive, but measured, unfolding over billions of years. Space itself grew, carrying galaxies with it, even as gravity worked locally to hold stars, clusters, and galactic structures together. The rhythm of this expansion shaped the cosmos, allowing structures to form and evolve without being torn apart. Galaxies drifted apart, their relative motion guided by the stretching of space. At the same time, local gravitational attraction bound clusters and filaments into the cosmic web. This interplay created the large-scale patterns observed today, vast filaments of galaxies separated by immense voids. Expansion set the stage for the universe's architecture, a dynamic equilibrium between separation and cohesion, motion and stability. Light traveling through space also reflected this growth. Photons emitted from stars and galaxies were stretched along with space itself, shifting toward longer wavelengths in a process called redshift. The universe's expansion left its imprint on light, allowing future observers to measure distances, velocities, and the rate of cosmic growth. Even the faint afterglow of the cosmic microwave background carries evidence of this gradual stretching, a subtle record of the universe's earliest expansion. The slow music of expansion also influenced the formation of galaxies and clusters. As distances between structures increased, interactions became less frequent, allowing galaxies to evolve more quietly within their local environments. Star formation, mergers, and rotational dynamics continued, but the expansion provided breathing room, preventing overcrowding and enabling stable, long-term development. The universe was learning to pace itself, creating complexity without chaos. Expansion also determined the distribution of matter. Regions with higher density remained gravitationally bound, while less dense areas stretched apart, forming the vast cosmic voids. The interplay of expansion and gravity produced the characteristic patterns of the cosmic web, an intricate network that spans the universe. Each filament, cluster, and void traces its origin to the balance between these two forces. a silent choreography that unfolded over billions of years. Even as space stretched endlessly, the universe maintained coherence. Structures held together despite the vast distances, demonstrating the subtle harmony between expansion and attraction. Stars ignited, galaxies rotated, and clusters remained bound, all moving within an ever-growing space. Expansion shaped not only the positions of objects, but also the context in which cosmic evolution occurred, providing the backdrop for all subsequent events. This slow music of expansion reminds us that the universe grows not through forceful explosions alone, but through steady, persistent change. The waltz of space carries galaxies, shapes patterns, and structures the cosmos over time, creating the framework for complexity to emerge. Expansion is silent yet absolute, a cosmic rhythm that has guided the universe from its earliest moments to the vast, structured expanse observed today. Beneath the visible universe, an invisible web holds everything together. This is dark matter, unseen, silent, yet essential. It does not shine, absorb, or reflect light, but its gravitational pull shapes the cosmos on the largest scales. Galaxies, clusters, and the vast filaments of the cosmic web all rely on dark matter for structure. Without it, the universe as we know it would not exist. Dark matter acts as the scaffolding of the cosmos. In the early universe, it clumped more quickly than ordinary matter because it interacts only through gravity, not through light or electromagnetic forces. These clumps formed gravitational wells, attracting gas and dust into regions where the first stars and galaxies could emerge. The ripples seeded during inflation were amplified by dark matter, creating the skeleton on which the luminous universe would hang. Invisible though it is, dark matter governs the motion of galaxies. Stars orbit within galactic halos at speeds that cannot be explained by visible mass alone. Clusters of galaxies move in ways that reveal the presence of far more matter than can be detected directly. Observations of gravitational lensing, where light bends around unseen mass, reveal the intricate patterns of dark matter, tracing an interwoven network across the cosmos. The cosmic web formed as filaments of dark matter stretched across vast expanses, with galaxies and clusters threading along these invisible lines. Voids, immense empty regions, exist between filaments, shaped by the distribution of dark matter. This unseen structure defines the large-scale arrangement of the universe, organizing matter into patterns that are both beautiful and orderly. Dark matter also influences cosmic evolution over time. Its gravitational pull regulates galaxy formation and cluster dynamics, affecting the growth of structures across billions of years. While ordinary matter forms stars, planets, and life, dark matter quietly maintains the framework, ensuring stability in an otherwise expanding universe. Its role is subtle, yet indispensable, a hidden architect of cosmic order. Though its nature remains a mystery, dark matter is central to understanding the universe. It demonstrates that much of reality is invisible, operating beyond direct perception. The galaxies we see, the stars we observe, and even the light that travels across space are shaped by this silent, unseen force. It is a reminder that the cosmos is governed as much by what cannot be seen as by what can. Through its quiet but persistent influence, dark matter connects the smallest galaxies to the largest structures. It holds clusters together, shapes filaments, and anchors the universe's architecture. Though invisible, it gives the cosmos coherence and stability. a web upon which the story of space and time unfolds. The unseen web of dark matter reveals a universe more complex and interconnected than appearance alone suggests. It is the silent framework behind every galaxy, the invisible stage upon which all cosmic evolution takes place, and a testament to the hidden forces that govern creation. Without dark matter, the universe would lack form, structure, and continuity. With it, the cosmos becomes a vast, organized, and evolving tapestry, stretching across space and time. The universe continues to expand, silent and vast, carrying galaxies, stars, and planets across space like leaves floating on an endless river. From the first subtle stirrings to the formation of cosmic structures, every stage has unfolded with quiet precision. The expansion of space, the flow of time, the guiding force of gravity, and the hidden presence of dark matter have shaped a cosmos that is vast, intricate, and ever-evolving. Every galaxy, every star, and every particle traces its origins to the earliest moments of creation. Tiny fluctuations in energy and density, amplified by gravity and guided by the passage of time, grew into immense cosmic structures. Invisible forces like dark matter provided the scaffolding, ensuring that the universe remained coherent even as it expanded. These processes demonstrate that creation often occurs quietly, patiently, and over unimaginable scales, producing order from what once seemed like nothing. The story of the cosmos is not only one of explosive events and spectacular phenomena, but also of the subtle, persistent mechanisms that operate behind the scenes. Expansion stretches space, redshifts light, and separates galaxies, while gravity binds matter into stars and clusters. Temperature regulates the formation of atoms, influencing the chemistry of the universe, and dark matter shapes the invisible web that holds everything together. Each force contributes in silence, yet the results are magnificent, forming a universe of breathtaking complexity. Even in emptiness, the universe is alive with potential. The spaces between galaxies, the voids across billions of light years, and the silent currents of dark matter all carry the imprints of its earliest growth. Observing the cosmos is like listening to a subtle symphony. Each note, each movement, reflects billions of years of evolution, stretching from the first expansion to the present. The universe has been writing its story in silence, leaving behind a record that can be traced in light, structure, and the very fabric of space. This expanding cosmos reminds us that creation does not always require noise or spectacle. The grandest structures emerge not through chaos alone, but through patient, persistent, and often invisible processes. From tiny seeds of galaxies to the vast cosmic web, from the first photons to the unseen threads of dark matter, the universe demonstrates the power of subtle forces acting over immense scales. As we look to the night sky, we witness the ongoing result of these processes. Galaxies drifting, stars shining, and the cosmos continuing to grow. Every point of light is a testament to billions of years of quiet evolution, to the unseen forces that sculpt space, and to the remarkable transformation from nothing into a universe capable of astonishing complexity. The universe is still expanding, still evolving, still composing its silent symphony. It carries the past, present, and future in every corner of space, and though much remains unseen, its story continues to unfold. The silent expansion is ongoing, a reminder that even in the vast emptiness, creation never ceases. The universe is alive, growing, and infinite, an eternal testament to the quiet power of existence itself. And so our journey through the universe comes to a pause, but the cosmos continues to grow and evolve, quietly stretching across space and time. Remember, every star, every galaxy, and every invisible thread of dark matter tells a story of creation. Thank you for joining me on this adventure. Please share in the comments where you are watching this documentary, and keep looking up. The universe has many more stories to tell.